All right, I think we've got a quorum here, or at least anybody else can probably catch it online if they wanted to. So this is going to be a sort of very general overview talk of trade-offs in fMRI acquisition. If you notice in the schedule, this is coming before the basics of fMRI, so what I've tried to do is actually put a little bit of that in at the beginning, just so that we all have the same vocabulary. I probably will miss a bunch of things. Feel free to ask me afterwards, come up talking to me, or actually send me an email about it. This is basically going to be about 10 lectures in one, so I'm hoping to basically convey a bunch of basic concepts and show a bunch of things on the slides. But if you're not catching everything, that's probably fine. Hopefully I'm getting enough across so that you're getting a good understanding of the various topics that I'm going to try to cover. So this is going to be sort of the outline of the talk. I'm going to give a basic introduction of voxel content, some of the signal basics, some of the bold signal basics for what's being acquired in fMRI. I'll move on to actual acquisition basics and talk about some spatial temporal resolution trade-offs in the acquisitions, and also finish with just different ways you can manipulate the functional contrast. In any of these topics, I think you can probably go to either to talks that are coming up in order to get any of these in a little bit more detail. So just to start us off and get this in perspective, this is a picture that I think a lot of people like to use. fMRI, which is what we're going to be talking about, happens to fall sort of in the middle in terms of millimeter resolution and a temporal resolution in the order of a couple of seconds. It's got basically better spatial resolution than EEG or MEG, which have considerably better temporal resolution. But it has better spatial resolution than PET, which has better specificity because you're using actual radioligands that bind specifically to various metabolite targets. But it does better than things like you don't really want to create lesions. It has a basically good compromise between spatial and temporal resolution in sort of encompassed in a non-invasive imaging method. In terms of where this talk is going to be placed in terms of the fMRI data pipeline, it's going to be right in the middle here, or at the beginning, in terms of we're going to be talking about what you can do in order to affect your data while you're scanning. So in order to do that, again, as I said, this is coming before the basic talk, so I'm going to give you a couple quick slides about some of the vocabulary of what's going to come up later. And really what I want you to take from it is that in the MR image, the contrast that we're getting, or what we're seeing, is coming from two things. It's coming from something called T1 relaxation time and T2 relaxation time, or T1 and T2 contrast. And we can play around with the T1 and T2 contrast, which are properties of tissues, in order to get various and change the grayscale that you see in the image. For example, the various types of tissue in the brain have slightly different T1s. Fat has shorter T1 than fluid does, and gray and white matter are in the center. And the same thing for T2. You have a split over all the different tissue types. With blood being closer to fluid and being kind of having a longer T2. And so really this just goes to say that you can play with the level of the T1 and T2 intensity, one by changing the repetition time, or TR, or the rate at which you're taking the images, and when you're taking the image in time. And notice that T2 contrast actually decays with time, so you have a limit on the amount of time that you have to acquire your image. So that's basically a very quick summary, and I invite you to come to, I guess, Vinay's talk on Friday. He should basically explain T1 and T2 contrast in a little bit more detail. So if we go take a step back and ask ourselves what's in a voxel, what we're actually imaging, there's a bunch of different things in a voxel. You've got the neurons, synapses, axons, and dendrites, which are basically what we would like to be imaging. What we are actually imaging, though, is a sort of a secondary signal, which is contained in the vascular capillaries, arterioles, etc. And if you compare the size of fMRI voxels, which are, say, for example, like 3 by 3 cubic, or if you look at this, it'll have an average voxel size of about 55 cubic millimeters. Inside a voxel of that size, you end up having 5.5 million neurons, 22 kilometers of dendrites, 220 kilometers of axons. I think that's roughly the distance between here and Philly. So there's a lot going on, and what we're getting is a very, very averaged signal. And since we're imaging, our signal is coming from vasculature, it's actually not even. This is over the cortical layers, which all have different input-output properties. And you can see that layer 3 has a little bit more density. And if you look at a cut here, I think this is through the visual cortex, you can see that there's one layer that has very, very much a higher density. So our signal is not going to be necessarily homogeneous across all of the brain tissue that we're imaging, because it's influenced by the vasculature. And that's basically the same slide here, just showing you cross-section through the gyrus. And lastly, we're really interested in what's going on in terms of the neurons, but since we're receiving the signal from or looking at the signal that's in the arterioles and veins, the coupling or the neurovascular coupling between the two things can be influenced by disease or also by drugs, for example, if you're giving somebody drugs and disrupting the coupling between the two things. To summarize what I was just talking about, if you give somebody a stimulus and you want to look at the neuronal activity, you've got the various things that are affecting each of the components of the signal, or each of the component chains of the signal. And we're really interested in measuring the blood flow, oxygenation level, volume, hematocrit, and also the things that we're going to be talking about mainly are here. These are the things that we can manipulate when we're at the scanner doing an fMRI scan. So the field strength, the TR, the TE, and the pulse sequence and image contrast. This is another summary slide that I had deleted before, but is still here. We're really looking, if we look at where the bold signal is actually coming from, if you go down into the veins and venules, you've got oxygenated blood coming in here at baseline, being exchanged in the capillary bed and going back out through the veins. In the active state, more oxygenated blood is coming in, and you basically get an oversupply of oxygenated blood, which is where the fMRI signal comes in. And so the oversupply of oxygenated blood gives you the difference in the signal, which is what we're actually measuring. So we're actually measuring something called T2 star, which is basically coming from the difference in blood oxygenation. But also note that it can come from a few other things that we will want to control. So I'll talk about that a bit later. So we'll move on to sort of the basics of MR acquisition. And going over some things like K-space, EPI spiral trajectories, and TR and TE. So going back to what fMRI, what we're doing in fMRI, most people are used to seeing anatomical images where you get one image every about 5 minutes. You get really nice resolution of the anatomy. You can even basically reconstruct somebody's face. But we're really interested in getting a lot of images over time. So if we want to get one image in 2 seconds, we basically sacrifice a lot of resolution, so we end up having a blurrier image than we would normally be used to seeing. But we actually then get to be able to measure sort of the brain activity over time. Unfortunately, more fortunately, it's just sort of a fact that instead of getting images in what you would normally be used to seeing, which is image space, we're actually acquiring something in reciprocal space. And this should be made more clear in a future lecture. But briefly, what it is basically the reciprocal space is sort of a listing of, or a weighting of all of the frequencies that are actually incorporated in the image. And I have an example of like a little movie that should make this a little bit more clear. There are different ways of acquiring the various data in these in the frequency space, and you can imagine what they are. There's some really obvious ways by just going in a raster straight across, or you can zigzag across. There's a radial pattern or a spiral pattern. really, we're mostly interested in two different types because those are the basic types that are mostly used. One is EPI, the other one is spiral. They're used because they drive the imaging gradients or the things that are making the noise in the scanner in an efficient fashion, particularly spiral. So what does this mean in terms of what this does to your image? So what you're going to see here is what is being acquired by the scanner, and it'll be directly basically Fourier transformed into image space as the acquisition goes. And in this case, it'll be sort of like EPI, so it'll kind of scroll down this way. You'll see that the high frequencies will come in, and you'll see the I'll just run it. Well, when I say I run it, I mean run it. You'll see the high frequencies are coming in as you go as you start at the outside, and as you come in the middle, that's where most of the very low spatial frequencies are, and the image will just pop into focus and just sort of sharpen as you go. So this is how an EPI acquisition goes, filling out the outside high spatial frequencies, and then all of the data happens to be in the middle. Just to have a look at what happens if you choose a different trajectory through k-space. So since most of the information is contained in the low frequencies in the middle, you might think that, well, acquiring that first is a good idea. So this is what happens if you do that, and I click to start the movie. Most of the image comes in from the center, and then you can see as the acquisition goes to the outsides, the image just gets sharper and sharper as the high spatial frequencies are included. I'll wait for that to finish. So what does that end up giving us? What does that translate to when we are actually looking at our images? These are examples of EPI images that are acquired like either across or up and down. And if they're acquired across, you end up retaining symmetry either right, left, or up and down. And you can see that there's slightly different holes in the image. These people have entirely full brains, but because of the susceptibility difference, or like because there's air and tissue have different magnetic properties, you end up having this artifact here, which is just a signal hole in different locations, which is just something to be aware of if you're interested in regions of the brain which are in the front. With spiral, though, you'll notice that like you're only acquiring data in the backside. So what happens if you just actually acquire another spiral on the front side without like you were not losing any time? If you do that, you can actually average those two images, and you can sort of get back some of the signal. So there are a couple of different tricks that people can do if they're interested in actually doing if they're interested in the regions that are really, really close to the frontal sinus. So now I'm going to move on to things that affect the sort of spatial temporal resolution trade-offs. And so in order I'll just reiterate that you have a really short period of time, or because the signal is decaying. And so you really only have that sort of that set period of time where you can actually acquire your signal. And if you don't get everything that you're interested in, you can basically wait again, like another, try to acquire it and excite the data again. So by doing that, what I mean is that you can either, acquire the whole brain at a low resolution, or you can just choose to actually focus on a couple of slices to shorten your TR, or also basically increase your in-plane resolution. If you increase your slice thickness in order to just sort of cover the entire brain, you increase your partial voluming. That means you basically you're averaging over white and gray matter, or CSF, and that's maybe not be something that you're interested in. But a lot of people will go for the whole brain coverage because they're interested in cognitive studies where they might not actually know what part of the brain they're active or looking for, or in the case of if they decide that they're only interested in the visual area or the motor cortex, they might just get one or two slices. So as I was saying before, you only get like a small window, which is 20 to 40 milliseconds to get the entire image. But if you do happen to want to get into like higher resolution, what you can do is just take 2 shots of the image. So in the first one, you get the first half of K-space. In the second one, you can get the second half of K-space. And you can play with like interleaving the various acquisitions if you'd like, or get quadrants if you want to do it 4 times. Obviously, what this does is it takes longer to get your image, so you're only going to be able to sample you're not going to get 2 seconds per sample. You'll have like 4 seconds or 6 seconds. But you do get a higher resolution. The other drawback is that you might incur a few more artifacts that you might not want. But with various improvements in MR acquisition technology, we now use multiple coils or multiple cameras, if you want to think of it that way, in order to get an image. And we can actually use the fact that each of these coils has a sensitivity profile, or it sees, if you want to put it this way, it sees various parts of the image, and we can use the fact that there's several of them and they're looking at the same image to do the same thing that we were trying before, which was like subsampling various parts of K-space, but we can do it at the same time. So now with the parallel imaging, we can actually get higher in-plane resolution. So as I was saying, you subsample K-space for each coil, and here you can see there's different coil, in a toy example, you've got different coil profiles, and then you select the parts that the coil sees best to reconstruct your image. So you get an acceleration factor, a factor of n, depending on how much you want to subsample your K-space. You can either do this in K-space itself, reconstruct the image in K-space itself, or you can do the same kind of game in image space, and they have different acronyms. One's called GRAPPA, one's called SENSE. The different vendors also have different names for the acceleration techniques. So the maximum acceleration is limited by the number of coils that you have. Sort of standard number of coils, they've got like 8 channel coils or 16, up to about 64 now. The penalty that you pay for this kind of acceleration, though, is obviously a reduction in the signal-to-noise properties, so you get a slightly noisier image. So now we've got good spatial resolution. What about temporal resolution? Well, they've come up with a solution for that, which is instead of getting one slice, they now excite multiple slices. And again, they're using a very similar trick by using the fact that you've got like coils at different positions in order to sort of unmix the slices. So the slices themselves, like the image that you end up getting from something that from a pulse sequence that does multi-slice or multi-band, is all the slices are sort of collapsed on top of one another, and they have to basically unmix the images, which they can do using a lot of math and some time. So one of the drawbacks is that it takes a long time to get these images, and there's still some artifacts that may still be in the image, but this technology has gotten pretty good, so you can get sub 2-second TRs with this. Obviously, this is an older slide deck. I've fixed a bunch of these errors. Anyway, again, the major drawback of this is that you're also losing, you're incurring a little bit more noise in order to be able to go faster. So that's a quick tour through being able to get high spatial and high temporal resolution. But of course, we're actually imaging an actual person, so there's actually some biological factors that are sort of limiting the spatial and temporal resolution that we can actually get. If we look at the effects of field strength, for example, because now they're coming out with stronger and stronger scanners. I think the standard clinical scanners maybe still at 1.5 Tesla. A lot of research now happens at 3 Tesla. As you go to higher field strengths, you do get higher signal, but you have a shorter T2 star or a shorter window in time in which to get the image that you're looking for. And you also have to wait for longer in order to get for that signal to recover. The other thing that you get is that there's more physiological noise. So the fact that the person is breathing and the fact that their heart is beating, because that sort of jiggles the brain a little bit, you end up getting a lot more of that kind of contamination in your image. So that means that it will sort of limit the voxel size that or the signal that you can get out of your voxel. If you wanted to consider what the optimal voxel size is, you're going to have to take into account those physiological fluctuations. If you had put a phantom in the scanner, for example, it's just going to sit there stably for as much time. So you get more signal, and you can average that over time. It's entirely fine. But you'll notice that if you actually put a person in, even if you get more signal than the artifacts that come from their breathing and their cardiac rate, that also increases. So you don't get a straight, like more signal does not mean that we actually can extract more of the fMRI signal that we're looking for. So people have come up with something that's called temporal SNR. So you may be familiar with the signal to noise ratio in normal images. This is sort of a temporal signal to noise relationship, and so there's people who have suggested that the optimal voxel size sort of matches the noise that you get from, say, the scanner, and making that equal to the noise that you would actually get from the person's heart rate or physiological rates. And so that is about, I think it's 1.8 millimeters is what they actually quoted in the paper at 3 Tesla. So you may get no further gains from either getting a bigger voxel or a smaller voxel in that case. Of course, if you remember from before, the sort of the way the vasculature is sort of distributed, you don't actually get a sort of even signal from across the imaging field. In fact, it's spread by about 3.5 millimeters from just like the signal that we're looking at. If you go to higher fields, you get sort of better spatial specificity. But of course, if you're thinking about actually doing a group study, which most people are, there's differences between people's brains. So if you're going to sort of average different people's brains, you might only have like 10 millimeters, which is just to say that we can actually acquire imaging, images at a resolution which is sort of smaller than the person-to-person variability. So when is the optimal time to take a picture? Obviously, you want to do that when the signal is strongest. But of course, the T2 star for our bold signal varies across the brain. So there's no optimal time that'll optimize it for every single part of the brain. And you can actually see that these are images that are taken at various different times or various different TEs, and they have slightly different contrast properties. Ideally, you want to acquire your image at TE equals T2 star, which is about 30 milliseconds at 3 Tesla, but it's sort of not going to be optimal for all the parts of the brain that you're interested in. But you have to compromise somehow. If you're also wondering how fast should I be acquiring my images, like what is the temporal resolution that I want? If you go really fast, you're sort of you're affected by inflow, so the blood is flowing through the image, so you're going to get some artifacts from that. Also, the hemodynamic response function acts as a filter, so it has a particular property here. So it basically takes about 6 seconds to get going, and so it limits the signals that you can see, or at least dampens them to sort of lower frequency signals. So even if you could scan really quickly, the hemodynamic response is sort of dampening out maybe some of the quicker signals that you're looking for. Moving towards what might be something that is an ideal sampling rate is maybe if you sampled the physiological noise so that there's no aliasing, so it doesn't sort of the high frequencies don't get smeared all the way across your image. Unfortunately, I don't think we're quite at the place where we can sort of scan at twice the heart rate of most people. If people have slower heart rates, maybe you can do that, but we're not quite at the point where we can actually go at twice the rate of a normal person's heart rate, which is about 60 beats per minute. Okay, so moving on to sort of the last section in terms of how to play with functional contrast. I think that Peter might have actually touched on some of this stuff in his talks on Monday. But I'm going to just go through a couple of different ones and hopefully give you sort of the basic idea and then try to describe them a little bit. So as I said before, the stimulus is happening sort of in the tissue and probably nearest to the actual capillaries and arteries, which is really what you want to measure. But standard Bold imaging basically is very sensitive to the large draining veins. And so if you were trying to increase the specificity of, or the resolution of the bold signal, you might want to just reduce the influence of the veins as a first guess. So that's what the spin echo technique is trying to do. So we've been talking principally about gradient echo stuff, maybe unbeknownst to you, but that basically measures like the T2 star characteristic of the bold signal. If you refocus some of the stuff that causes the star on the T2 star, you get a straight T2 signal, which is what spin echo is doing. You can basically increase your specificity, as I was saying before, and I'll describe a little bit on the next slide. But you end up reducing the number of slices that you get per TR. You also get a slightly reduced contrast to noise signal. So the reason that this works is that the larger veins also have like this. They sort of have a susceptibility associated with them, and so they also create their own little magnetic field gradient, which spin echo can actually compensate for, basically, for the larger veins, but not so much for the smaller veins. So it ends up being sensitive to smaller veins, whereas gradient echo stuff, which is the sort of standard stock sequence, is actually sensitive to all of the bigger veins as well. So a practical application of this is, if you remember the vascular density changes across, say, the visual cortex, so there's one layer which is really, really dense. You can image this, for example. I think this is in a cat. So they've done both gradient echo and spin echo images here. You can see that the gradient echo images are much more sensitive to the draining veins, which are on the top of the peel surface here. Whereas in spin echo, the contributions from those veins are basically reduced considerably, and you now start being able to see the signal that's from the tissue, which should be closer to the activation that you're actually interested in. Okay, so another way of doing it as well, of maybe increasing the specificity of your signal as well, if blood is the problem, because blood is draining into the draining veins, why don't you just null the blood signal? And this technique is called vascular space occupancy technique. If you want, Laurentius really likes this technique. He's sitting there. You can go and ask him questions about this later. I actually got his slides from him. So if you remember, basically tissue and blood have slightly different T1 properties. So you can play with these properties and get it to a point where where the tissue is slightly faster than the blood in terms of recovering from various manipulations. So you can actually get to a point where blood is actually zero. And if you take a difference image at that point, you can basically just get signal from the tissue. You'll notice from this little graph here that there's only exactly one point where the blood signal is zero, which means you can only get one slice at a time. But you're still getting something where the blood is completely suppressed. So hopefully you're getting information that you're looking for, which is a little bit more specific than just the bold signal. And it's just a negative contrast. And here's an example of that. And you might be asking yourself, well, is it really more specific or is it just less sensitive? Actually in terms of vaso, it's actually more sensitive. So you'll see right here, if you compare the bold image to the vaso image, you can see that the large veins have sort of contaminated and sort of blurred the bold signal, whereas it's not so. You can actually see two sides of the sulci. You can see the sulcus between the two gyri here. Same thing on the other side, where instead of a positive influence, you've got a negative cancellation. This is sort of useful for if you're interested in doing layer-dependent fMRI. You can actually distinguish between the two sides of the sulcus, and you get really nice resolution that way. So if you want to get more than one slice at a time, you might, instead of nulling the blood signal, you can maybe tag the blood signal, and that is called arterial spin labeling. Briefly, what you do is you sort of tag the blood as it comes into the brain. You wait a little while, and you image the tagged blood. And you take a subtraction between these two images, and you should get the blood which actually was activated. So if you compare the two the bold sequence in the ASL, basically in the end you get more signal around the veins for bold, whereas you get a reduced signal for ASL, but it's more evenly distributed across the tissue. Or at least hopefully that's what it is. So if you actually look at an example, you can see in this case, this is the motor cortex. There's more bold signal. There's slightly less here, but it's hopefully a little bit more specific because the signal is mostly from the arterioles and the capillaries. Problems with this are that it takes a little bit longer to acquire, so you can't get as many slices. You have slightly lower signal, but what you do get is lower intersubject variability, and it's insensitive to the drift artifact, which sort of is something that happens, and that gives you trouble with slow stimuli in fMRI. So if you look at this is something that's switching on and off every 30 seconds, for example. Pretty good in bold, pretty good in ASL. You can see the signal difference here and here. This one's got higher signal. But what happens if you start playing out stimuli that are, say, a minute long or 2 minutes long, and you can see that sort of the bold response is dropping off, even though you can see that the subject is actually still doing the task in ASL. So that's one of the problems with sort of standard fMRI, that you have a couple of specific task frequencies that you have to be able to pick, and if you wanted to do things like learning task or something like that, you won't be able to resolve that so well, but you can with ASL. Okay, so we're only taking one image at one particular point in this signal decay point, just right here. But you can see that there's a signal difference here and there's a signal difference here. So what happens if you measure at more than one point? And because we have the ability to accelerate our image acquisition, we can do this now. And that's multi-echo fMRI. And the nice thing about this is that you can actually separate bold signals from the non-bold signals. Because the bold signal sort of varies as a function of when you take when you get the image, so as a function of like TE. On the other hand, non-bold signals don't actually scale with the TE. So if you do measure at several TEs, you can make this nice difference curve. It doesn't like my fingers. You get this nice difference curve, and you might be able to separate something from something that the signal which actually scales with the echo time versus something that doesn't. And an example of that is here. So say you're doing a visual task here where you've got an on and off signal. You can see that there's 3 different echo times, 15, 39, and 63 milliseconds. And at each of these echo times, you can see that the signal is scaling pretty nicely. So this is actually a real signal that's happening. And the same thing can be done for resting state fMRI. The nice thing about that is all of the artifact, as I said, they don't scale. They look exactly the same at each of the echo times versus something that is more signal based or more sort of it's a bold signal that we're looking to measure. It actually scales with the signal. So if you sort of ranked those, if you ranked the sort of image components as a function of whether they do or do not scale with the 3 echo times that you're taking in this particular case, you can pull out all of the like resting state networks that will be talked about later and separate them from all of the noise that we don't necessarily want. And this basically gives you the ability to image those slow signals that you were that you couldn't do before when I showed you the comparison with the bold and the ASL. You can basically, this is sort of the standard technique. You can see that it does pretty well with sort of the block design. You can still see the block design in the normal signal. But when you do a slow signal, basically you see a flat line. If you use some multi-echo with multi-echo denoising in the way I sort of described before, you can actually resolve that slow signal again. And if you look at the non-bold components, you can see why the signal is disappeared, because a negative slope and a positive slope basically add to nothing. And the other advantage of multi-echo is, if you recall, I said that the TE varies, or the T2 star varies across the brain. Here you're taking multiple images at multiple TEs, and so you can average those to try to get basically the best signal across the brain that you can possibly get for your bullet signal. All right, so in summary, hopefully I've sort of given you a bit of an idea of the spatial temporal resolution trade-offs, as well as the various ways in which you can manipulate the contrast in order to try to get at the neural signal that we're looking for, despite the fact that bold is typically something that's sort of like a little bit removed from neural activity. And an appreciation of the fact that the bold contrast is, or just the standard gradient echo EPI is not the only thing you can do, that you have multiple other contrast choices. Also, I think that with like the advances in the hardware and technical and software and reconstruction abilities, we're basically approaching the ability to acquire the fMRI scans at a pretty high temporal and spatial resolution. And now we just have to sort of figure out exactly where the origins of the fMRI signal are to sort of get the most out of this technique, and hopefully it can then be much more useful clinically. With that, there's some acknowledgments. My email address is there if you want to ask me any questions. And I'll refer you to sort of the talks that are coming that will actually basically go into all of the topics that I discussed in probably much more detail. There's probably actually one talk on perfusion, like ASL, and one talk on the basics, and one talk on the advanced acquisition. So hopefully this gives you an idea of what's coming in the rest of the course. And with that, I'll take any questions. I was asked to ask people asking questions to come up to the mic because apparently they're recording this, and then you can be internet famous.
So I had a question. So there's a lot of stuff going on about how to sample the case space, right? And I was wondering whether people also have thought about maybe playing with different types of resolutions within one scan, within one repetition, possibly even, for different parts of the brain. Like you probably want to have a different resolution for the amygdala or the hippocampus than for the prefrontal cortex.
Yeah, I mean, I'm aware of at least some, like there's I think Eric Wong is now doing something where instead of going across the brain, or going across case space in a regular fashion, he's actually trying to just sample specific networks. So he basically designs a pulse sequence to image specific regions in like he does the Fourier transform, figures out, like, say, the resting state default network. He does the inverse Fourier transform, has that pattern in K-space, and just samples that because it's a lot less. You're right. It's a lot less points or fewer points, and so you can image that really quickly. So there are people who are trying to go in that direction. Of course, that means you have to know exactly what it is you want to image, and that's really the problem. Like if you know specifically what you want to image, then yeah, maybe you can do that. Also, there's things like variable density spirals because you want to get more information in the center, so you densely sample the center and you sparsely sample the outside. So there are those kinds of tricks. So if there aren't any more questions, you can go, or you can, if you're too shy to ask questions, feel free to come up and ask me questions.